All right, so here's an example. In a case study of the biodiversity of trees in a tropical rainforest, the number of tree species, let's call that S, was plotted against the area, let's call that A in meters squared, on a log plot. The result was a straight line with a slope of 0.84 and a vertical axis intercept. Notice they don't say y-intercept. The reason they don't say y-intercept is because it's not necessarily the y-intercept, it might be the log of y. So they're trying to be very kind of cagey to say it's the vertical axis intercept. Of negative 0.06. We want to find the equation that relates for species as a function of area. Okay, so that's the whole build up. Now, there's a lot of words there. We don't need all these words. So when I see a question like this, where they're asking me to find the species as a function of area, I'm kind of trying to identify the key things here. And so what I see is, well, we have species plotted against area on a log plot. And what we got was a slope of 0.84 and a vertical axis intercept of negative 0.06. So those are the pertinent pieces of information. So now I'm trying to write my equation here. Well, I guess I might draw the graph first. So the graph of this looks something like the following. This has got a negative intercept. So I'm going to draw something like this. Here's my line, where my slope is 0.84, and that intercept there is going to be negative 0.06. Now, something else to consider here, since it's a log plot, we know that one of these axes is log of something, and the other axis is log of something. Now, which axis is which? If I want to write species as a function of area, which should be my vertical axis? Species or area? Good question. So the thing that's the function of the other thing is typically your vertical axis, and the input thing is typically your horizontal axis. So I'm thinking of this as being the species axis, and this as being the area. But it's really not just species, it's log of S. And this one is going to be log of A. That's what we really have here. So if I'm trying to write this equation, I could write it as log of S equals 0.84 times log of A plus negative 0.06. Or I should write minus, but I write plus here. So that's what we're starting with. And then typically we're required to write it without any logarithms. So we have to solve for S. So usually we're going to write both sides as 10 to a power. Now, it might be, I think it might be worthwhile if you've got a log of A here to go ahead and bring this 0.84 up as the exponent right there. So I might, even before writing both sides as 10 to a power of, right, this is log of S equal to log of A to the 0.84 power plus, do it again, negative 0.06. And now we can write both sides as powers of 10. So I can write this as really 10 to the all of that equal to 10 to all of that. 10 to the log of s is just s. Question.
Why is the negative 0.06?
Why is it a part of the exponent? So the way I would say it kind of is basically whatever you do to one side of the equation, you have to do to the entire other side of the equation. It's kind of like the reason why the square root of 5 squared plus 4 squared isn't 5 plus 4. Because when you're saying like x squared equals 5 squared, plus 4 squared. If I take the square root of both sides, I have to take the square root of the entire other side there. Like that. So more generally, whenever you apply a function to both sides, it's to the entire thing. So then, but then we're going to break it up. So 10 to the log of this plus that is really 10 to the log of a to the 0.84 times 10 to the negative 0.06. And then 10 to the log of some stuff is that stuff. So we can really write this as s equal to a to the 0.84 times 10 to the negative 0.06. I would probably leave it like that, but some people like to write the 10 first. You could rewrite this as s as a function of a, if you really want to, is equal to 10 to the negative 0.06 times a to the 0.84. Notably, not surprisingly, a power function, because your variable is being raised to a power. And we always expect to get a power function if our linear relationship was a log-log linear relationship. Whereas if it was semi-log, we would expect to get something exponential. So questions about any of that before we do a couple more examples? I didn't. Yeah, you could. 1 over 10 to the positive 0.06. Definitely, yeah. That would be totally good. Let's see, I feel like I had another. Yeah, let's do one more like this, and then we'll do a couple. We'll do one, maybe two, where we do all the like on Google Sheets kind of stuff. Because I think that's worthwhile to see again. Did your teacher talk about how to do it in using Google Sheets? She did. Great, awesome, good. I would expect that, but let me see. Let's do this next one a little bit more boiled down to just the bare minimum here. So let's say we have a population P over time T, and the data falls on a straight line, no big surprise there, with a slope of m equal to 0.41, and at time equal to 0, the population is equal to 60. Find the population as a function of time. Oh, I missed one very important word, and I'm sorry. Falls on a straight, so the data on a semi-log plot. Oof. Sorry about that. Falls on a straight line with a slope of 0.41 and has the point t equals 0, p equals 60. You don't need to draw a graph of this, but it doesn't hurt. So you can totally skip the graph part. I think it's worthwhile. So here we know, since it's semi-log, your x-axis or your horizontal axis is just the regular variable, in this case t, the input being time. And the vertical axis is not p, but log of p. And our line looks something like this. It's got a slope of 0.41. And I will point out that this point here is not 0,60. This point here is 0, log of 60. Because when t equals 0, p equals 60, which means this point is log of 60. So be careful. Sometimes problems try to be a little tricky like that. But then we can do the usual thing. We can say, okay, well, our output log of P is equal to, again, it's going to be mx plus b, or in this case, m times t plus the input's going to be log of 60.
Log 16, where would it be?
So, good question. Let's say we did this instead. Let's say we had log of P equal to 0.41 T plus just 60. If we plug in T equals 0, then we're left with log of P equal to 0 plus 60.
Use like the y-intercept.
Right, exactly. So instead, what we wanted this to be was we wanted this to be log of 60, so that when we plugged in T equal to 0, we actually got P equal to 60, not P equal to log of 60, or not log of P equal to 60. Yeah. But yeah, the plus B here, that is just your y-intercept, whatever it is. And then it's the same sort of process, just now we're going to, all right, 1 second here. Now we're going to have a different looking answer, but we're still going to raise both sides to a power of 10. So I'm going to say 10 to the log of P equals 10 to the 0.41 T plus log of 60. And just like before, all of this stuff on the right-hand side is in your exponent. And since there's addition, and there's almost always going to be either addition or subtraction, you can always break it up into two pieces multiplied together. On the left-hand side, 10 to the log of P is just P. On the right-hand side, we've got 10 to the 0.41 T times 10 to the log of 60. Couple things people usually do here. Typically, we're gonna simply, so normally, a lot of times this is not very nice. Sometimes it's like 10 to the 5 or 10 to the 5.37. But if it's 10 to the log of 60, that's just 60. And here, we usually rewrite this as 10 to the 0.41 all to the tth power. If I was writing this, I would write this as P of T. I would probably write the 60 first, just because that's fairly standard, times 10 to the 0.41 all to the tth power. And the reason you might write it this way specifically is to emphasize the exponential nature of the relationship. You've got essentially y equal to some c times b to the t. That's the idea, is why we're writing it that way as opposed to some earlier version of it. So just to say this again, or again from last Thursday, when you have a log that has a linear graph, it ends up being a power function like the previous example. When you have a semi-log relationship that is linear, it ends up being an exponential function like we have here. Yeah, question. Sorry. If you're raising your hand, I'm like, yeah, you can just say, hey, James, what's up?
I didn't know that the T was the x-axis and then y.
Really the way I knew was, I mean, generally time is the x-axis, but really specifically in this problem, regardless of what they're calling things, when they say find P of T, that to me says, oh, T is the input, which is the horizontal axis, and P of T is the output, which is the vertical axis. So whenever they're talking about writing one thing as a function of another thing, the thing we're a function of is the input horizontal axis, and the thing that's the function, the output, is the vertical axis. Bless you. But yeah, good point. So let's talk about how you would do one of these problems that I have from another person. Just coming up. Just 1 second. I'm pretty sure we did number 6 last time, so let's take a look at number 7. So here is a problem from a different professor from a while ago. following table is based on a functional relationship between x and y that has either an exponential or a power function, meaning either it's semi-log straight line or log straight line. So our job is to figure out which it's going to be. And then they say use an appropriate transformation, blah, 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 blah. Basically, you're going to do that. And again, you can do this using Desmos. I feel like I would say the one thing I like about the Google Sheets method of doing it versus the Desmos method is the Google Sheets gives you the equation of the linear relationship, which then you have to go back and do the work of changing it back to the functional relationship. So I think it's probably better practice for you to do it using Google Sheets than doing Desmos. That said, do whatever you want. So, but I'm gonna take all that data. I think I copied it. Let me double check. Copy, and then just go over to Google Sheets. Let's get a new Google Sheet. I know there's a plus sign right here somewhere. There it is. And we're just going to copy or paste that data. Come on. Why would you be so annoying? Try it again. No, wow, what the heck? I know. Sometimes you just have to type it in, which is super annoying. Let me try again though. Let's try one more time. What if I start here? I know it shouldn't make a difference. No, wow. Okay. Gosh. Okay, fine. Let me do it over here. So typing things in. I do think it's worthwhile to name your columns. So I've got X, 0, 2.5, 3.8, 4.2, 5.4. And then my Y values are going to be less nice, but fine. I've got 15.4, 98.4, gee, who came up with these numbers? 47, 258.1987, 347.4096, and finally 846.2621. Cool. And so then we want to, and why fine? Okay, fine. Let's see. It's hard to see. Let me actually turn down the brightness, maybe. Or not. I'm really smart. Let me turn down the brightness of this thing here. That's not at all. Sorry. Sometimes the brain gets a little tired. So then we want to leave a column empty. Otherwise, things get totally screwed up if you have columns. If you have things next to other things, I don't know why, it doesn't work. So over here, we want to do X versus log of Y. So we're going to call this X. And this is just going to be the same as the first column. So that's going to be A2. And then we're just going to drag that down. And then same here, we want log of Y. So I'm going to call this log of Y. And then I'm just going to say this is equal to log of Y. Not log of Y though, log of B2. Right? B2? B2. You do need the parentheses. If you don't have the parentheses, it won't give you the value. And then it wants to fill it in. Great. Thank you so much. I will take it. And then we're also going to want log of X versus log of Y. Actually, what I would say is I would do this first before I do the next part, just because maybe this is going to be the right one. And you're going to get R squared equal to 1 perfectly. And so you might as well see if this one gives you what you want before you check the second. So let's go ahead and grab all this. I do recommend grabbing the column names as well. Really hard to see. Oh, there we go. Okay. We're going to insert chart. There's our chart, and then we're going to be smart about it. We're going to customize. We go to series. We go down to trend line. Looks pretty good. Looks like a perfect fit, but we're going to double check by asking for showing R squared. R squared is 1. That's the one we want. And then, of course, we need the equation. So we go back to the, I can even see it here, the label, I think. It's really hard to see. And use the equation. So there's our equation. Our equation, I'm going to write it down over here. Our equation for this data is going to be log of Y equal to 0.321x plus 1.19. And I'm not going to check the other one because I know this is it. You can't have a better value than R squared equal to 1, so we shouldn't do more work than we need to. Then after that, we then want to answer this question, which is, gosh, where'd you go? Why would you do that? All right, I think I closed it. Apologies. Someday. Someday, my principal. Why? Did I think I did the wrong thing there? Okay, fine. This is problem 7. So we want to solve your relationship for y in terms of x. Okay, so right now we've got this. We've got log of y equal to 0.321 x plus 1.19. Well, we've got practice solving this. We know what to do. We're going to write both sides as powers of 10. So 10 to the log of y is equal to 10 to the 0.321x plus, oops, sorry, that plus should be up in the exponent, plus 1.19. Technically, you could probably just leave your answer like this. If you wrote it as 10 to the 0.321x plus 1.19, if you're throwing that into web work, that's going to be fine. I personally like to simplify it more because usually that's what's expected of us. So I would do the 2 steps of writing it as y equal to 10 to the 0.321x times 10 to the 1.19. And then I like to rewrite this as 10 to the 0.321 to the x power. And that would be my answer. Sometimes people like to actually get approximate values for these. Just using a calculator here real quick. 10 to the 1.19 is about 15.48. And 10 to the 0.321 is, let's find out. About 2.094. So I'm curious if we enter that, if it'll be right. Just, I think it's worth checking. So let's go ahead and find out. Oh, I see what I did. So if I'm going to try plugging that in, 2.09 times, oh, sorry, 2.09 to the x, apologize, times a 15.48. Let's preview my answer, make sure it looks okay. All right, looks all right. Let's see what happens if I submit it. It might not come out right. Nope, it didn't. So I should have used the exact values, right? Those decimal approximations were not close enough. So if that's not going to work, I'm just going to go back in and write my actual answer as it was, right? I'm going to write it like this. So let's see, that's going to be, all right, 10 to the 0.321 to the x, and then times 10 to the 1.19. Sorry, 1.19. Let's preview that answer. Cool, looks good, I think. Yeah, let's submit it. Success. So sometimes a decimal approximation is not going to cut it. Sometimes it will. It really depends on kind of the things your professor might have said.
When I do on a Google Sheet and I click insert to get the chart,
Yeah.
it gives me like 2 different scatter.
Interesting. So do you have other data next to that data?
I do.
So I don't know why, but you need, for whatever reason, your 2 columns of data, you want an intercolumn between them. Otherwise, things go wacky. I don't know why, but it's like trying to read it in a different way. So it came from a lot of why isn't this working? But yeah, as long as you put an empty column between every pair of xy or x log y or log x log y, you're safe.
And then when I copy the new, like the log x and log y,
So and probably because it's referring back to, like, for example, so I close my Google Sheet. No, I didn't, just in here. So let's move this here. So like you're trying to like copy like maybe this. Copy that and then say paste it over here. Seems to work out. but what I'm typically doing, so like if I wanted log x, so you maybe want log x and log y, is that what we're wanting here? So I'm going to call this log of x. And then the way we get what we want, oh, well, there's a problem here. The problem here is that if you do log of this value, log of 0 is undefined. That might be what's an issue. I don't actually know. But the way I'm getting what I want is always just taking, so like if I want this to be actually log of 2.5, I'm going to ignore the first two columns. If I want that to be log of 2.5, I'm going to say equals log of, and then I'm going to plug in, yeah, D3, that's what I want. So typically the reason you get the ref error is because it's just not, it's referring back to something that doesn't make sense to input, which might be a 0 or a negative number if you're trying to do logarithms, or this might be something that doesn't make sense in some other way, like characters or whatever. So notice when I'm doing this, I'm not writing that this is equal to log of x because that's just the name of that column. I don't need it to be a formula. When you use an equal sign in Google Sheets, the Google Sheet is expecting you to write some sort of formula for the thing you're calculating based on other cells. Other questions about this? Yeah. Okay. Interesting. Okay. So like all this work is working out for you and you're getting like you're getting like the equation here with an r squared equal to 1. And then, just let me ask, what's your equation that you're getting? Yeah. Well, no, what's this equation right here on your Google Sheet? I'm curious. And let me ask you, plus 1.05. Was that your log y versus x, or your log y versus log x? Are you sure? It's okay if let me just double check. I want you, because here's the thing, this is one of the things that's confusing. That one? Yeah. Okay, cool. You're good. Yeah. So, let's take a look. So then it's worth exploring this. So if this was our equation, and again, that's what log. So I know. Here's it, just so everyone's clear though. If we were to, I apologize. If we were, let's say the log y versus x one wasn't the right one. R squared was like 0.85. So then we went to check the log x versus log y one. I'm just going to delete this. Yeah, it's annoying. Sorry, this row here is not helping me out here. Sure, I'm just going to leave that as a 0, even though it's not right. But let's say I was going to try and plot this one. So I would do the same thing. I would insert a chart. And really, you do it this time? Usually when I do this, for whatever reason, it doesn't show log. Oh, no, that's all. No, that's fine. It shows log y versus log x. Okay, I'm thinking it's nails. But then when you go get the when you go try to get the formula for the line, that's pretty good. Not as good, but pretty good. And then the label, I want to point out that the equation doesn't say log of x right there, but your equation should. So if you're doing the log one, you should be writing log of y equals 0.528 times log of x plus 0.781. So just be careful though, right? It's easy to miss that small thing if you're getting the log one. So that's why I was worried that might be the case, but it's not the case. Shireen?
Yeah, it will always do that with the log or with also log, semi-log, sorry.
What do you mean? Like
with the log next to the x?
No, so for log, it's because we're plotting log of y versus log of x. But for semi-log, we are plotting log of y versus x. So we just want regular x there, like the equation is already written. So it's just kind of an unfortunate fact that they don't call the input x variable the thing we would like it to be called in this other equation here, but it is. So back to your question, Dana, why isn't what you're getting working? So let's take a look. So if we were going to solve this, we would have to do the normal thing. So we're going to write 10 to the log of y equal to 10 to the all this. And as is usual, when we break this up, we're gonna get y equal to 10 to the 0.477 to the x times 10 to the 1.05. So that's what should be correct if you're entering it. Is that what you're entering? I'm curious. Okay. Oh, what? Let's see what the problem says.
I thought I had this.
I'm not sure. Because I'm getting the same thing.
I think with that, you just have to use the.
So the only thing I think might be the case is that you might have to actually write it the way I've written it, not so like do the next. Yeah, I'm not sure. We'll have to look at it. We can look at it after class. But yeah, I don't know why it's not coming up right, because that seems like it should be correct. Yeah.
If it's 0.447 log x, how would you spell it?
Sure. So if it was log of y equal to 0.447 log of x plus 1.05, just pretending like we've gotten this from a log graph, then we're still doing the same thing. We're going to write 10 to the log of y equal to 10 to the 0.477 times log of x plus 1.05. And then I personally think we should simplify this because I don't know, it's good to see the actual simplified relationship. Also, also for this one, the question does specify your answer shouldn't have any logs in it. So this one here, we definitely need to get rid of the log. 10 to the log of y is just y. And here we have, well, I'm going to point out that this 0.477 can come up as the power of x on the logarithm. So that we have 10 to the log of x to the 0.477 times 10 to the 1.05. Right, because it's 10 to the this plus that. And then 10 to the log of x to the 0.477 is just x to the 0.477 times a little bit more than 10. That's how we would write this one if it was log versus being semi-log. Yeah. Mm-hmm. Well, sure. So I could have totally, because of it's actually not, it's not based on what semi-log versus log, it's based on the phrasing of the question. So here the phrasing of the question said we had a vertical axis intercept. Also, I wouldn't have really said here that at, say, for example, when a equals 0, s equals something, because you can't take log of 0. It's the problem. So here it often gets phrased this way because of that. Whereas with the semi-log, I could have said, semi-log. I could have phrased it like I did and said, we know that time equals 0, p equals 60. But I could have said, alternatively, I know that my vertical axis intercept is, I'm going to make up a number that's useful here. Oh my God, just give me the, oh, you done this, sorry. Not you all, I wrote log of 60, like how to solve your problem? I just wanted an approximation of log of 60. Oh, there we go, 1.77. I could have said that instead. And then we would have done log of p equals 0.41 plus t plus just 1.77. So there's different, it's not about whether it's semi-log versus log, it's about the phrasing. If they say vertical axis intercept, we know that's just our b, the plus b that we're adding in your y with mx is b. Whereas if they say at time equals 0, or when your input is 0, your output is this much, then we have to be more careful about what we actually have here, because the y-axis is really log of your variable, so you need to have log.
So like log, then that would never be 0 because that's something possible.
Right, exactly. Good observation. Yeah.
Yeah, just making sure that if you get like 0 is one of the things you have to use semi-log.
Typically, yeah. So that's actually a good clue, right? On your homework, if your data has a 0 on the X side, probably not going to be log. Can't take log as 0. Yeah, good questions. Other questions about this? Should we do one more example? Okay, let's do one more, and then we will move on because we should talk about a lot of stuff. Let's go grab this other example. Sorry, keep losing my place here. So great, here's another one. So it could be log or semi-log, same sort of deal. I'm going to, of course, try to copy and paste this data. I'm not confident it's going to work because Google Sheets is just being unkind. Can we just pull up a new sheet? Let's just delete it all. Fine, that's not what I meant to do. Fine. New? Yeah, new. Great, thank you. Why? Oh, sorry. Sorry, it's hard to see all the things. So let's see if this works this time. Not confident, just hopeful. Nope, of course not. Okay. So we'll go and grab the data. I really wonder why. If I just did this instead. Oh, I have a better idea. Let's try this. Right over there. Maybe so I've got one idea. Let's try that. Nope, okay. But what if I did this instead? Nope, still didn't work. Okay, fine. You win this time, Google Sheets. How bothersome. Let's see. I mean, it's not that terrible, but it's not great. Let me just pull it over here. So here's our data. We've got 1.7 for X, 2.1, 3.9, 4.5, 5.1. For Y, we similarly have 3.0491, 2.0494, 0.3429, 0.1890, 0.1041. Okay, same deal. I'm always going to do the log one for the semi-log one first, just because it's really easy to copy, right? If I just say that this is A1, and then just copy everything down here. And then I want this to be log of Y. So I'm just going to call log of Y, and then this to equal log of B2. You could probably even set up like a whole thing where it just automatically did it once you put in your data in the right spot. That's probably not worth taking the time to do that because there's not that many problems. And then I'm guessing here it's probably going to be log. So I'm also going to want log of X. And that's just going to equal log of D2 or B2, take your pick. And then grab it and pull it down. And same deal here, we want this just to equal E2. Yep, thanks. Why is it not giving me the last value there? Oh, interesting. What should be? Yeah, but I want it to be that. Oh, because I'm using a formula and I'm not being smart about it. Ooh, yeah, don't use formulas when you don't want numbers. And then I want this to equal. Oh, and I said E2 and not E1. That's actually probably why. If I actually set this equal to E1, it should work. Yeah, there we go. Thanks, Shereen. I think that's what you're trying to say. I just wasn't hearing you. There we go. Same values. Usual process. Grab these things. And yeah, gosh, it's good. And then insert a chart. Guess my points are on there somewhere. You say so. And it doesn't feel like they're on there, does it? Like I don't see the points like we usually do. But let's see what happens when we try to get our stuff. So we want the trend line. Yeah, I'm curious about what's going on here. I feel, I'm not feeling this. Does that feel right? Does it feel like this doesn't feel right. Yeah, I don't know. Can we delete this? Yeah. Sorry, it just feels like that was the wrong thing. Let's try one more time. Okay. It's the same. But I don't see the points. Do you guys see the points? Am I just crazy? Yeah, that's weird. Okay, well, it said R was equal 1, but let's check the other one just to be sure. Because I feel like, I don't know. We check this one instead. It's just, oh, I know, it's just giving me a weird, like, it's not giving me this kind of chart I expected. I don't know why. Right, yeah. So that's in the customize. Sure. Sorry, I'm not sure what you mean. On the right side. Oh, thank you. Up here. Oh, maybe, yeah. Good call. Thank you so much. It's gonna really bother me. So then same deal here. We should be able to. There we go. So that looks more normal. And then you would do the whole line thing. And I've got too many charts now. Why do they all say the same thing? Anyway. So it does look like this one was the right one. So let's try that again. Why are you being funky? There we go. And now if we find the usual things by customizing and finding the usual deal. There's your trend line, looks excellent. R value is 1 as expected. And the equation, which is actually what we need, is always impossible to find. So there's our equation. We've got log of y, and it is semi-log here, right? Because it's log of y versus x, so it's log of y equal to negative 0.431x plus 1.22. And then it's the same thing we've done quite a few times, right? You're going to say 10 to the this equals 10 to the that. You're going to have y equal to 10 to the negative 0.431 to the x times 10 to the 1.22. And that should work. And again, I'm not sure why those other ones aren't working for you also. Definitely after class, I don't have anything after this until like 3:30, so I'm happy to stick around and look at stuff. Oh, do you know what? Okay, well, fine. When did this is due? Wednesday, okay. I'm available Wednesday. What time is it due at? Okay, I definitely have office hours tomorrow, so come find me. I'm happy to help. I don't know why it's not working. Okay. So log, semi-log, okay, question.
Know if it's R² equals 1.
So really, these are designed to come out to be perfectly linear. Like really what someone probably did was they took actually some power or some exponential equation and found some data points is what they probably did. So if you get values here real quick, just to kind of point out, like, I don't know what these numbers actually are, but let's see, 10 to the negative 0.431 is about 0.37. I mean, really, I think some of these were generated by web work. And then 10 to the 1.22 is is about 16.6. So what someone or some computer probably did was that, okay, this is my actual relationship, and then they found values of X and values of Y, and then they took log of the Y values and left the X values alone to get this nice semi-log data that perfectly fit a line. That's what I would do. So like if I was trying to come up with data, which I've done before, I come up with something that is like a power function, for example. Like I might start with Y equal to 1.1 to the X times 4.3, and then I'm going to make some X and Y values, and then since I know it's going to be semi-log because it's exponential, I'm going to actually find the X and the log of Y values. And that's the data I'm going to give you. And that data will perfectly fit a line on a semi-log graph, which is when you're going to get R squared equal to 1. More broadly, if you were doing this and you're just trying to figure out which was the better fit and it wasn't a perfect fit, you would pick whichever R squared value was closer to 1. So if one of them's like 0.95 and then one's like 0.87, you pick the 0.95.
Like on a test, like how would they?
You would never do this on a test. The type of question that you would get asked on a test more likely is the one we started with, where they're like, here's your relationship that's linear on a semi-log graph, work backwards to find the functional relationship. Or they kind of have to, yeah. Yeah. All good questions. Like you guys are asking really smart questions about this stuff. But I don't know why we dedicate quite so much effort to it, but it's not interesting. It just feels like a kind of a lot to do. And then, okay, let's move on. So speaking of moving on, I guess I should ask before we move on and start talking about sequences, I should ask for the homework in section 1.5, which is the one that's due tomorrow, which is somewhere in my notes somewhere. Yeah. Are there any other questions specifically about like the log stuff or the exponential stuff? Yeah. Sure. Like the one with the e to the 3x or the e to the 5x or yeah, that one's a little wonky. Let me show you how to do the one that I have here, just because I think it's not too terrible once we see what's going on. So let's look at this numbers. And I guess I should and then I'll get to everybody. Well, I'll get to as many people as I can. So let's see. We have the function f of x equal to e to the 5x over 9 plus 6 e to the 5x. So normally when you start this sort of thing, you're like, okay, I'm going to write this as y and then an interchange. So in an interchange, we're going to get x equal to e to the 3y over 9 plus 6 e to the 3y. And normally our stated goal at this point is to isolate y. Right, so I didn't show the part where I'm calling this y and then interchanging x and y. That's how we find the inverse function. We interchange x and y, and then we solve for y. But I'm going to point out that your intermediate goal before solving for y is we're going to try to isolate not y, but e to the 3y. Since I have multiple instances of them, I have to kind of do that before I can get y by itself. Oh, I am so sorry. I'm like, this seems like a lot of confused looking faces. Let me explain this more. Yeah, sorry. I looked at it and I was like, that looks like a 3 to me. Yeah, that's a 5. Thank you very much. Apologies. Sorry about that. Please, if I write something dumb like that, don't hesitate to speak up. All right, so we're trying to isolate e to the 5y. Good times. And then after we isolate e to the 5y, then we can solve for y. So first things first, you almost always want to get rid of the denominator. So we're going to have x times 9 plus 6 e to the 5y equal to e to the 5y. And to be able to isolate e to the 5y, we have to get all the e to the 5y's on the same side. To do that, we're going to have to distribute the x here. So we're going to get 9 times x plus 6 times x times e to the 5y. I would put the x there because that just feels normal to me. And then I'm going to bring all the things that have e to the 5y on the same side. So I'm going to subtract this over there. Say 9x equals e to the 5y minus 6x times e to the 5y. And then I'm going to factor out the thing I'm trying to isolate. So I'm going to have 9x equal to e to the 5y times 1 minus 6x. And then I've met my intermediate goal after I divide both sides by 1 minus 6x. So 9x over 1 minus 6x is equal to e to the 5y. Check. Now, after I've done that, I can solve for y. So I have e to the 5y equal to 9x over 1 minus 6x. Then I'm going to take the natural log of both sides, because that's how I undo an e to the something. I'm going to say that the natural log of e to the 5y is equal to the natural log of 9x over 1 minus 6x. The natural log of e to a thing is just the thing. That's why we do that. So 5y is equal to the natural log of 9x over 1 minus 6x. And then finally, multiply both sides by 1/5 or divide both sides by 5 and say that y is equal to 1/5 times the natural log of 9x over 1 minus 6x. It's pretty typical. It's a little, I should say, it's a little atypical because usually it seems easier to solve for y. You can't solve for y here until you've gotten e to the 5y isolated, and then you can solve for y. Cool. What else? What other questions? I know I saw a few other hands with other potential questions. But I wrote down a bunch of things. Don't know if we're gonna get the sequences today. Sorry. We'll definitely get the sequences on Thursday, and we'll talk about sequences and lines. So, Dan?
Number probably 6, there's like the last 3 questions are like the one that has like L is.
Sure. Yeah, that one's kind of weird, I think. So if we look at something like that, so the one I have is the natural log of x cubed minus 7 times the natural log of x equal to 1. So what I would say is that when you're trying to solve a logarithmic equation like this, if you've got multiple logarithms, we want to combine them together. Problem is we can't combine them together until they have the same coefficient. So the first thing I want to do is I want to take this 7 and bring it up as the power here. So I want to write this as the natural log of x cubed minus the natural log of x to the 7 equal to 1. And now I can combine those logarithms because they have the same, or I guess say they're subtracted together and they have the same coefficient. This is 1 natural log of x cubed minus 1 natural log of x to the 7. I'm not really writing that or thinking of it, but that's what I have. Now, when I have a logarithm minus another logarithm, I can combine that into 1 logarithm, natural log of what? Exactly. You all know what to say. Divide x to the 3rd divided by x to the 7. I want to point out it's not natural log of x cubed over natural log of x to the 7. It is the natural log of the quantity x cubed divided by x to the 7. Okay. I would probably do one more simplification before I rewrite this. And actually, I'm going to do 2 things. So first of all, x to the 7th, sorry, x to the 3rd over x to the 7th. You can either think of it as x to the negative 4th or 1 over x to the 4th. So that, I'm going to write it as 1 over x to the 4th. And just to be super extra clear, I would normally write natural log, but I want to remind you all that natural log is just an abbreviation for the log base e. Okay. So I'm going to rewrite this as an exponential equation. And I know I've said it probably 100 times already, but here's the one I always keep in mind. Log base 2 of 8 equals 3 is equivalent to, literally means the same thing as, what's my base? What's my power? What's it equal to? Right. Same deal here. What's my base? What's my power? What's it equal to? I don't know why I wrote this. I didn't mean to write parentheses there, but it just kind of happened. So that's what I've got. E equals 1 over x to the 4th. I don't really want to write it as x to the negative 4th. What I really want to do is just take the reciprocal of both sides. It's totally valid. If you don't like that, you could multiply both sides by x to the 4th and then divide both sides by e. But I will point out that literally gets us to the same place as if we had done the reciprocal of both sides. It is a totally valid operation. If two fractions are equal to each other, their flips are also equal to each other. Okay, so now if I'm going to solve for x, let me ask you all a question. I know we've had deep discussions about this. What's the solution to x squared equals 25? I said, what are the solutions to x squared equal to 25? Right, exactly, plus or minus 5. So if we were being extra careful, even though it's going to be a problem for us, the solutions to x to the fourth equal to a number, a positive number, should be x equal to plus or minus the fourth root of 1 over e. Because if you take the positive fourth root of 1 over e and raise it to the fourth power, it's going to be 1 over e. If you take the negative fourth root of 1 over e and multiply it by itself 4 times, a negative times a negative times a negative times a negative is positive. Now here's the problem. The negative one isn't a solution. Because if you go back and look at the original equation, this was the original equation. And if you plug x equal to negative number in there, you can't take the natural log of a negative number. So here, what I want to point out is that x equal to positive fourth root of 1 over e, or as you probably want to enter in your web work, or x equal to 1 over e to the 1/4 power is our solution. And x equal to negative fourth root of 1 over e is not. It's called an extraneous solution. Sometimes you introduce the possibility of extra solutions when you simplify a logarithmic expression. Actually, specifically when you, no, that's not true. So, okay. Okay, we have 10 minutes. So, yeah.
It's not a solution because there can't be a negative number.
Because we can't take the natural log of a negative number or I can't take any log of a negative number or 0. Yeah. Right.
And the log e that you did.
Log base e, yes.
Base e is the same thing as just e to that one. Right?
No. So what I'm really saying here is I'm saying that the natural log of whatever you like is the same thing as log base e of whatever you like. This is just an abbreviated shorthand notation. The reason I rewrote it this way was just to make it extra clear that I could rewrite this as e to the first equal to 1 over x to the fourth. I could have done that here as well. I could have said, oh, there's a base of e there. I just didn't write it. Raised to the first power equals that. But I just want everyone to be super clear. Like, for example, if I said, what's the natural log of e to the 7th power? Well, it's easier to know what this is if we remind ourselves that the natural log is really just the log with base e. And then you're saying e to the what equals e to the 7th. Now, you might prefer to view this as the natural log and the e to the whatever undoing what each other does. But the reason this is really working, well, actually, another way you could do this is say, if you want to take a longer path, you can say this is 7 times, right? The 7 can come down, log base e of e. And log base e of e is 1. But I could also have written this as 7 times the natural log of e. It means the same thing. The natural log of e is also 1. These are the same, they're just written differently. So the natural log of x is the same as the log base e of x. All this is an abbreviation. It's an abbreviation in the same way that the log of x, when you don't write a base, is really the log base 10. So it's just really out of space saving and laziness. It comes up so often that we decided we don't want to write 1, 2, 3, 4 letters when we could write 1, 2 letters instead. But that's all it is. Really. It's just an abbreviation. There's nothing special about it other than e is a special number. Sure. Let me explain the extraneous solution through another example. Let me see. I know I can come up with one real quick. Yes. So let's say we wanted to solve. All right, one moment. Sure. let's say we had log base 2 of x plus 5 plus log base 2 of, I gotta be careful here, one moment, I want 3, sure. Sure, x plus 1 equal to 5. Let's say I wanted to solve this. So if I was going to solve this, I would put it together and say, okay, great. Log base 2 of, I'm going to multiply those together. So x plus 5 times x plus 1 equals 5. And I'm going to rewrite it. 2 to the 5th equals x plus 5 times x plus 1. I'm going to multiply it out. 2 to the 5th is 32. And x plus 5 times x plus 1 multiplies out as x squared plus 6x plus 5. Subtract 32. 5 minus 32 is negative 27. This does factor. This factors as x plus 9 times x minus 3. So what are my possible solutions? Right. Now here's the thing. These solutions would totally be okay right here. Because 3 plus 5 is 8, 3 plus 1 is 4, and 8 times 4 is 32. And negative 9 would also be totally fine right here. Because negative 9 plus 5 is negative 4, and negative 9 plus 1 is negative 8, and negative 4 times negative 8 is 32, which is positive before you take the logarithm. The problem is, this is our original equation. If you try plugging in negative 9 here, negative 9 plus 9 is, negative 9 plus 5 is negative 4. And it doesn't work to take the log of negative 4. So x equal to negative 9 is extraneous. Because even though it solves some later version of our equation, it doesn't solve the original version of our equation. Another sillier example would be, here's an equation, x equals 3. I know this sounds dumb. What's the solution? 3. But if I square both sides, now there's 2 solutions, plus or minus 3. But minus 3 isn't a solution to the original equation. So often when you square both sides or raise both sides to an even power, you also introduce the possibility of an extraneous solution. So it just means a solution that you got kind of later on after you did some stuff, but does not solve the original equation. Typically not. I don't think the intention of that problem was to have to check for it, because it doesn't end up being, like, most people would kind of overlook the plus or minus anyway. But yeah, that's what I would say. Yeah, only even powers of roots are where you kind of really have to worry about that. Yeah.
So on the other problem,
Mm-hmm.
LNX,
Yeah.
at the part where, when we're at the ln x cubed over x7,
Mm-hmm.
why can't I, well, am I able to just do e on both sides?
Sure. Yes. You could totally, I just wanted to I really wanted to emphasize the nature of the fact that when you rewrite a logarithm expression, but yeah, you could totally have said that this is really e to the natural log of 1 over x to the 4th equals e to the 1. And then that just becomes 1 over x to the 4th equal to e. That's also totally good way of thinking about it. Okay, let's see here. I feel like there was one other thing I wanted to make sure I hit on before we get going here, but we're almost out of time. Oh yeah, let's look at this. Let's look at this one more interesting equation. Let's say we had something like, sure, I want to solve e to the the 2x minus 9 e to the x plus 20 equal to 0. So the idea here is that this is technically looking kind of like a quadratic equation. This really looks like e to the x squared minus 9 times e to the x plus 20 equal to 0. some people like to do like a substitution here where they call this like y or something. I don't think that's particularly necessary. We're just looking for numbers that multiply to 20 and add up to -9. I think -4 and -5 fit the bill. So this can factor as e to the x minus 4 times e to the x minus 5 equal to 0. You could, if you wanted to, say, I'm going to let y equal e to the x, and then write this as like y squared minus 9y plus 20 equal to 0, and then factor it as y minus 4 times y minus 5 equal to 0, and then plug back in y equal to e to the x. So e to the x minus 4 times e to the x minus 5. That's a more convoluted way of doing it, I think, but it's totally legitimate. Either way, once you've set something equal to 0 and factored it, then we're just setting each factor equal to 0. So we're going to set e to the x minus 4 equal to 0, which gives us e to the x equal to 4, and e to the x minus 5 equal to 0, which gives us e to the x equal to 5. And then to solve this, I'm going to take the natural log of both sides. So the natural log of e to the x equals the natural log of 4. So we get x equal to the natural log of 4. And same deal here. We're going to get the natural log of e to the x equal to the natural log of 5. X equals the natural log of 5.